lenses, there are different types of lenses. So one first we come across is a convex lens, right? So convex lens is also called as a biconvex lens, right? You can see here concave lens like this. So apart from this also we can have another kind of lenses like this. So this is plano concave lens and another one is plano convex lens. This is plano convex lens. This is plano concave lens. You can get it. So another type of lens we come across, concave or convex lens. Right, so there are the different types of lenses we come across, and we can learn how the light rays is passing through that, what are the sign conventions, and a lens formula, and we'll go for lens maker formula, and thin lenses, and combination of lenses. All these things we can obtain from here. A spherical reflecting surface is a part of a sphere of refracting material. Now let us see this, how these light rays are passing through a refracting surface of having a certain refractive index. Now let us see here. There is a convex surface, convex refracting surface. This is a concave refracting surface, right? So here is, if you consider it is air medium, and this is a certain medium of glass. Otherwise it is a rarer medium, and this is a denser medium like this. Now let us see how these light rays are passing, and here also we consider a center of curvature and a pole or optical center here, right? So from pole you can see these things here. So this is this curved surface is a part of a sphere. Obviously it will have a center. That center you call it as center of curvature, and that distance you note it as a radius here. In the same way here also same thing. But one thing you can notice that in case of convex surface, the center of curvature is inside that medium. Then whereas in case of concave surface, the center of curvature is outside the medium, right? So then now let us see this. Before going to this some derivations, we need to have some assumptions and some conventions, right? So first assumptions, let us see. Object is at the point lying on the principal axis. So first we will take that a point object we keep at the principal axis, and the light incident ray refracted with small angles, right? We'll consider that. Then aperture is also so small. So by considering all these things, assumptions, we derive equations, right? We shall see how these derivations will be obtained. The incident ray is taken from the left to right. Of course, you can take right to left, but the convention will be different. Then all the distances will be measured from the pole of the refractance. So just like in the mirror, here also what we do is from the pole also only you have to measure. Then distances measured in the direction of incident ray, as like in the previous one. Distances measured in the direction of incident ray are taken as positive, and distances measured in opposite to the direction of incident ray are taken as a negative, right? Then the distances measured above the principal axis is taken as positive, and below the principal axis are taken as a negative. So by considering these conventions, let us go for an equation of refracting surfaces, right? So now let us consider a rarer medium and a denser medium. This is pole and is center of curvature. Refractive index is mu2. This is mu2 for denser medium and mu1 for rarer medium. Now this is a principal focus. And now let us take an object at O. Then light ray obtained from the object O and if incident on this refracting surface are undergoing a refraction like this. Actually, because of this refraction and this surface, because of this medium interface and the surface, it undergo refraction and went towards this principal axis and it forms image at I. right? So let us take this NC is a normal. So usually it is 90 degree, no? So when a light ray passing through a center of curvature is perpendicular to the surface, like this. Then now let us see here. If such is the case, then angle between this normal and incident ray is I, angle I will take it here, right? Then let us draw AM. Then let us take this is a angle refracted angle of refraction. That is, if this is an incident ray and it will undergo like this. So angle between this normal and this refracted ray is taken as R, or angle of refraction here. And for our convenience, let us take this as alpha and let us take this as beta, and we will see this, and this is gamma. Let us take this, right? And this distance between P and C is taken as a radius of curvature R. And whereas since the object is at O, and already I told you distance should be measured from the pole, then P to O is taken as a U. And similarly, the distance where the image forms at I, so distance between P and I is taken as a V. Now let us see here. Now let us take tan alpha. Alpha is this, right? Tan alpha is AM by OM, is opposite by adjacent. That's what we have taken here. Now let us take, and for small angles, the tan alpha can be taken as alpha. Therefore, alpha can be written as MA by OE. That's what it is. Then let us take tan beta here. Tan beta is this, and tan beta is equal to AM by MI. That's what we will take it. Then for small angles, we take beta is equal to MA by MI. Then similarly for gamma, this is gamma, right? So that is opposite AM, and this distance is MC. That is tan gamma is equal to MA by MC. Then for small angles, we can write gamma is equal to MA by MC. Then let us see here I, angle I. Here this is angle I. Okay, this angle I can be taken as, right. So this is angle I. Okay, this angle is equal to, you can see this triangle AOC here. Okay, triangle AOC is the exterior angle I is the exterior angle for triangle AOC. So therefore angle I can be written as angle A plus gamma. Angle A plus gamma you can take here, right? Angle A plus gamma. Then similarly, now let us go for this angle gamma can be written as, here you can see this, right. This angle gamma can be written is an exterior angle for this triangle ACI. So therefore angle gamma is equal to angle beta plus angle R. That's what we write here, angle beta plus angle R. Then therefore R can be written as, angle R can be written as, angle R can be written as like this. So gamma minus beta you can take it. So then using Snell's law, we can write sin I by sin R is equal to mu2 into mu2 by mu1. Otherwise, even sometimes you can use this for simple application. Mu1 into sin I is equal to mu2 into sin R. R can be taken. So therefore, if you substitute here, mu1 by mu1 into sin I is equal to sin I, right? So sin I by sin R is equal to mu2 by mu1 you can write it. So therefore here for small angles you can write I by R is equal to mu2 by mu1. That is mu1 into I is equal to mu R. Otherwise here also you can write directly this one, mu1 into I is equal to mu2 into R for small angles, right? So substituting I, R, alpha and gamma by replacing M and P. See, actually here one thing what we have measured, no, O to P is okay, well and good, no problem. But whereas in case of measurement of CP and measurement of IP, we take in place of IM and IC. In here IM, you're measuring, so we write it as IP here. And whereas MC will write it as a CP. And substituting in this equation, in this equation, you will get like this: mu1 by PO plus mu2 by PI is equal to mu2 minus mu1 by PC. Here you see. Substituting this angle I, alpha plus gamma, and R is equal to Y minus beta. And solving that, we get mu1 by Pi plus mu2 by Pi is equal to mu2 minus mu1 by PC. Right? And after that, here what we do is, as I will consider that sign convention. So object is in the left side of P. That is opposite to the direction of incident ray. That should be taken as positive. Sorry, negative. That should be taken as negative. And these things should be taken as positive. So therefore, PO is minus U and PI is positive. And PC is also positive. So therefore, you substitute in this here minus U you substitute, and here you substitute V, and here you substitute R. Then you will get this equation: mu1 by minus U plus mu2 by V is equal to mu2 minus mu1 by R. So either you can remember this equation. So most problem, very easy to remember this equation, right? So this equation we can remember. Right? So this equation we can take it. Okay, so mu1 by PO plus mu2 by PI is equal to mu2 minus mu1 by PC. This is refractive index of first medium and the object distance, that is PO, and refractive index of mu2 and the image distance, that is PI, is equal to mu2 minus mu1, that is denser medium minus refractive index of denser medium minus refractive index of rarer medium by PC. PC is what a radius of curvature. That will take it. Right? Once again, you will use the convention, sign convention. Here, wonderful thing is this sign convention, this mu1 by minus U plus mu2 by V is equal to mu2 minus mu1 by R. This you can use it for concave surface also. Same equation, same thing, but if you use it for concave surface, you can use same equation, you can use it. This is for convex surface, and similarly let us go for concave surface. What is the equation? Same equation, mu1 by minus U plus mu2 by V is equal to mu2 minus mu1 by R. Here also same thing, mu1 by minus U plus mu2 by V is equal to mu2 minus mu1 by R. Right? So, but one more small clarification I would like to give here, that if you take an object is inside the denser medium, like this. If you take object inside this medium and the image obtained here, then the small changes we can notice that. So where you will have to change mu2 here. In the previous one it was mu1. Here it is mu2 was there. Sorry. In the previous one it is mu1 and this is mu2. Whereas here the same thing. So where mu1 and mu2 will be interchanged, only that much. Otherwise everything is same. Right? So if you take the object in a denser medium, you will write this equation. That is mu2 means first. In another way also you can remember that. So refractive index of first medium by object distance with minus sign plus refractive index of second medium by image distance, and refractive index of first medium minus second medium. Sorry, refractive index of second medium minus first medium by R will take it here. Right? This is for even for convex surface as well as concave surface also. Right? So therefore, here now you see this. You compare these two here. Refractive index of convex surface for denser medium to rarer medium for virtual image. Refractive index at concave surface for denser medium to rarer medium for virtual image. So all these three equations are written. This is for if an object is inside the medium or in a denser medium. You will use these equations. Right? Now, same things. So once again we are going to repeating here the expression for object in a rarer medium. expression for object in a denser medium. We'll take this. Here, what are the changes you can notice? Here it is mu1, here it is mu2, whereas here it is mu2, here it is mu1. So therefore, here mu2 minus mu1, here mu1 minus mu2. Right? If an object is in a denser medium, then we'll take refractive index of a rarer medium with object distance with minus sign, and refractive index of a denser medium with image distance, that is equal to mu2 minus mu1 by r. So overall, in simple way we can understand that. So object distance, right? So first one is object refractive index by object distance with minus sign, right? Then image refractive index by image distance, and image refractive index minus object refractive index by radius of curvature. Right? Here also same thing, you can see this, because here in this case object is inside this. Object is inside this. So here is object. Go like this, either it forms image or virtual image forms image. So therefore here object, this is mu2 here. This is mu2 and this is mu1. So this is object refractive index of object medium to the object distance, and refractive index of this image medium, that is mu1 by v, that is equal to then second medium minus first medium, that is image medium refractive index of second medium to the refractive index of first medium, right? This is first medium or object medium, or this is taken as second medium. Therefore mu1 minus mu2 by r, we'll take it here like this. So in this way you can remember, right? And this is same for both concave as well as convex. So first one is, I shall repeat this. This is for concave as well as convex, and this is also for concave as well as convex. And this is if object is in a rarer medium. If object is in a rarer medium, here is object and it forms image here like this. Then this is for rarer medium. This is for denser medium. If the object is in denser medium, we'll take this thing. And this lens maker formula is in another way you can, the word itself will make you to understand. Suppose you are giving an order for an industrial person to make a particular focal length of glass. Then what he has to do it. Suppose he is having certain glass of certain refractive index. Then he has to cut that in the form of a lens, such that required amount of focal length it should have, a required length of focal length it should have. So therefore what he has to see, if you know the refractive index, then if you know the radius of curvature, then what particular radius of curvature, if you use it, then you will get a particular focal length lens. So that, like that you can notice here. So in this way, here is your lens. Now let us see that what is the focal length of this one, right? Otherwise, to have it is having certain radius of curvature. This is for R1 and this is for R2, right? And where this is a refractive index mu2, and where outside one is mu1, that is air, right? So let us take this is a principal axis, and where P1 and P2 are the points on the surface which the principal axis is passing through it. Then where C is optical center, right? Where C is optical center, and C1 is a center of curvature and C2 is a center of curvature. But this C1 is center of curvature for this surface, right? And C2 is the center of curvature for this surface, right? So therefore, if an object is at O, let us see this how this image forms. So now what we'll do is we forget about this surface, the second surface, that is LP2N. You forget it, only you consider this surface, and by considering this surface and applying these formulas, okay, let us consider this surface here, and this is a complete a glass medium, let us consider here. And this is let us consider a complete glass medium and a convex surface here. So complete convex surface, then if image forms here at this. Forget about this the another surface, let L, P2 and N. Now what we do is this I1 is considered as a virtual object for this another surface, that is L, P2 and N. Then what will happen? Now for the time being you forget other one, that is L, P1 and N. Then due to presence of this surface, then it forms an image here at this position. Let us see now, right? It forms image at I here, right? So now let us take one by one and see that how these image form. Now if you consider only first surface, that is LP1N, if you consider this surface only, and applying that the previous formula, that is mu1 by CO, that is the object refractive index of object medium, this is mu1, and object distance, that is OC will consider. Then similarly the image distance, here image distance for this surface, is I1. So therefore we will write it here mu2 by Ci1, and mu2 minus mu1 by Cc1. This is Cc1 is this, right? Cc1, that is radius of curvature for this surface. Okay. So then after this what we'll see is we consider this is an object for this surface, that is LP2N. Then we apply the same the previous formula if an object is inside that medium. Okay, but one small thing is that it is a virtual image. So because of that, what you can consider here, it is mu2 by Ci1 will consider here. Consider mu2 by Ci1 plus mu1 by Ci. Right? This is image. This is object distance, but in this refractive medium. Consider it is in because light traveling in this one. You can see, just a minute. I'll tell you. So here light is traveling in this medium. It means that it is in a denser medium. Denser medium to it is moving outside this. So therefore we consider this is mu2 object distance, object medium, right? Refractive index of object medium by object distance. Refractive index of image medium by image distance is equal to, here you write it as mu1 minus mu2, right? That is outside this mu1 minus mu2 will consider. So therefore here what will happen, if you take this minus sign inside and here you take this one and you will call this equation number 1 and call this equation number 2, right? And adding these two together, right? By adding these two together, then we will get this thing here. You can see here. That is mu1 by CO, you will get it. So these two get cancelled here. Let us see this. Mu2 by Ci1 and mu2 by Ci1 get cancelled. Then what is left out is mu1 by CO. That's what we will write here. Right? Then mu1 by Ci. That's what we write here. And if you take this minus inside, we will write it as mu2 minus mu1. Similar to this. Right? So this is mu2 minus mu1. If you take this minus inside, then mu2 minus mu1 only. Then Cc2. And you can take this mu2 minus mu1 outside this bracket. Then what is left out is 1 by C1 plus 1 by Cc2. Then using one sign convention here, same conventions, right? So same convention is light. This if this measurement, it should be taken as negative. These measurements are taken as positive from C here, right? Then by taking this, object distance will be taken as negative, u minus u should be taken, and the image distance should be taken as positive, that is v plus vv should be taken. And whereas r1 and r2, this is r1 is taken as positive and r2 is taken as negative. And substituting in this equation, you see here CO is object distance u is taken as negative here. Then v CI is v but positive, you can take it here. And mu2 minus 1 as it is, right? And mu1 is here. then you take this common outside and bring it to the denominator, then you will get here. Then 1 by r1, 1 by r1 is taken as positive because it is in this direction, positive direction, along the direction of incident ray. Then r2 should be taken as negative because it opposite to the direction. So therefore, suppose and next thing is that here, if you keep the object at infinity, right, then the image forms at f. Suppose this you take it as v, object distance u should be taken as infinity, then image distance will be taken as a f. So if 1 by infinity is 0, 0 plus 1 by f, you will get this equation, right? So here mu2 by mu1 is equal to mu. Otherwise, sometimes it is also got mu2 with respect to 1, right? So then our equation can be written like this: 1 by minus u plus 1 by u is v is equal to mu2 with respect to 1 minus 1 by r1 minus 1 by r2. Same thing you can write it in this manner also. But here one thing you can do. Suppose if you keep the object at infinity, suppose let me write the figure here once again, no problem, right? If you consider this is lens, right? If the object is at infinity, somewhere infinity, the image forms at f. So therefore, if u is equal to infinity, then v is equal to f, right? So same thing if you apply here. So here if you put infinity, then you have to put f here, right? So therefore 1 by infinity is 0, then plus 1 by f is equal to, you will get this thing. So therefore the above equation once again can be written like this. That is 1 by f is equal to mu2 with respect to 1 minus 1 into 1 by r1 minus 1 by r2, right? So otherwise this is called as a lens maker formula, right? And another thing is let me clarify your doubt that suppose some people are writing like this mu2 with respect to 1, or some people will be written like this mu2 1, some people will write it mu2 with respect to 1 like this. All one are the same, no need to hesitate, right? And you write it in any manner, but even sometimes in different question paper also have these kind of things. Even instead of mu, some people may write like this also: mu2 with respect to 1, sorry, n2 with respect to 1, n2 with respect to 1 like this, or n2 with respect to 1 also like this, right? So it's all one and the same. So whichever may be, then you can take that, right? So then otherwise by taking this here 1 by minus v u plus 1 by v as 1 by f, you can get this equation mu2 with respect to 1 minus 1. So this equation is called as lens maker formula. And you can any lens maker has to use this so that he can prepare a particular focal length. Suppose if the refractiveness of the glass is known, then he has to choose r1 and r2. And usually what they do is this is r1. Suppose if you consider the above figure itself, right? So then there will be r1. This is r1, and this will be r2 for this curvature r2, right? r1 and r2 usually it will be equal. So that is why it's called as biconvex lens. Most of the cases it is r1 and r2 will be equal. But you can see while taking this r2 is it is taken as a negative and r1 will be taken as positive. And when you substitute here, this will become positive, minus of minus. This is already positive. Then add it together. While taking calculation, don't subtract each other and make it 0. Okay. So therefore, while substituting this, you can do it. And next question is it true for concave lens also? Or else is it any different equation do you have? No. Everything is same. Same lens maker formula will be applicable for concave lens as well as. But only thing is while taking R1 and R2, it should be very careful. You should be very careful. So using that same convention, you also substitute and you will get that. Right. Now let us go for thin lens formula, or usually it is called as a lens formula. Right. Now let us consider a lens here, and it is having two surfaces of radius of curvature 1 and radius of curvature R2. Then here you see this is optical center, denoted by C, and most of the cases it is denoted with O. Now a principal axis passing through this optical center. Then here is F1 and 2F1, F2 and 2F2 here. Right? So let us keep an object between 2F1 and F1 here. Then it forms an image here like this. So a light ray parallel to principal axis passing through after refracting through the lens, it will passes through F2 and it go like this. The same way light ray passing through center of curvature. So without deviation it goes, and but these two rays intersect each other, forms image here. That is called as A dash B dash. Right. So this distance is object distance where you keep the object and the optical center, and the image distance is the distance between image and optical center here like this. And the distance between this principal focus F2 and C is F will be taken, and this distance between 2F and C will be taken as R here. Right. And one thing is that let us consider that R1 and R2 are same here. Now let us see here, consider triangle ABC and A dash B dash C. ABC, this is, and A dash B dash C, this one. Right. So here you can see that these two angles, you see these two angles, this angle and this angle are equal because vertical opposite angle, and these two angles are also equal, and these two angles, that is ABC and A dash B dash C. So since the two angles of these two triangles, corresponding angles are equal, then obviously third angle also equals, and otherwise also these two triangles are similar. Once these two are similar, we can say that the ratio of the sides, the ratio of the corresponding sides of these two similar triangles are equal. So that's we can take it here. That is A dash B dash by AB is equal to B dash C by BC. Right? A dash B dash by AB, A dash B dash by AB, then B dash C B dash by BC will be taken, BC or CB. Right? Similarly, now let us take another triangle here, triangle A dash B dash F2 and triangle MCF2. Right? And here also in this these two triangles, we can prove that these two angles are equal, because vertical opposite angles, and these two angles are also equal because perpendicular angles, and hence two angles are equal, and obviously third angle is also equal, otherwise also these two triangles are similar. So therefore corresponding the property of similar triangles, by using that we can write it as A dash B dash by MC is equal to B dash F2 by CF2 will take it. Right? A dash B dash by MC is equal to B dash F2 by CF2. Right? This is corresponding sides. So then one more small change we do is that instead of using MC, in place of MC, I write AB here. Right? And now you see the equation, this equation, let me call this equation 1, and let me call this equation 2. Right? So taking these two equations, right, comparing these two equations, left hand sides are equal, obviously right hand sides must be equal. So therefore we can write it as CB dash by CB is equal to B dash F2 by CF2. That's what here. Right? And BF2 here, B dash F2. This we can write it as B dash C minus F2C, you can write it here. Right? B dash C or CB dash minus CF2. Right? By remaining things are same. Right? Then substituting these values, what is CB dash? CB dash is image distance, and it is in this direction, should be taken positive. And CB is object distance, it is in this left side of the C, so therefore it should be taken as negative. Right? And CB dash same, positive, but UV minus CF2 is F, principal focus F2, so therefore CF2 is F will be taken, but it is positive. And substituting here, CB will be minus U positive V U, CB dash is plus V, and CF2 is plus F. Substituting this, we'll write this one. V by minus U is equal to V minus F by F. Then in simplification, we can write it as, so V by minus U, as it is, we'll write. But one more thing, what we do is multiply by 1 by V, both sides. Then here one more step you will take it, that is V by F minus 1 you will get it. Multiply throughout by V, you will get 1 by U is equal to 1 by F minus 1 by V. So therefore the same equation can be done like this. 1 by V minus 1 by U is equal to 1 by F. Right? So therefore this formula is called as what? Thin lens formula, or else lens formula usually it is called. Right. So similar to this magnification in mirror, here also it will define like this. It is a ratio of height of the image to the height of the object. That is m is equal to hi by h naught. Then the previous figure we can write it as a dash b dash by ab is cb dash by cb. So according to Cartesian coordinates sign convention, we can write a dash b dash is 1 if you take size, I or h if you take I, and AB you take it as minus O, then plus V by plus U. Otherwise here you can take it as I by, instead of I by O, if you take it as HI by HO, you can write it as V by U here. Right, here minus minus get cancelled, then you left with V by U. Right, so magnification, if you know V and F, you can use this formula for magnification. M is equal to F minus V by F. If you know U, you can use this formula. M is equal to F by F minus U. Right. So more quickly you can find the magnification, or else if you know magnification, you can use these to find F and U. Right. Then after that, let us pass on to another concept, that is power of lens. Right. So power of lens, it is the ability of a lens to converge the light rays or diverge the light rays. So in case of a convex mirror, the light will be converged like this, and whereas in case of diverged mirror, the light will be diverged. Diverged mirror in the sense, in case of convex lens, the light rays will be converged, and whereas in case of a concave lens, the light rays will be diverged. Then how best they will be diverged, or how best it will be converged, that will be taken into account, right? And it will be defined in another manner, but before that we'll take this definition. The power of lens can be written as P is equal to 1 by F. And more systematic manner, let us see this, what the power of lens is. Right? So power of lens is a measure of convergence or divergence of lens. Right? How best it will diverge or how best it is converged. Then it can be defined in another way. That is, the power P of a lens is defined as the tangent of angle by which it converges or diverges a beam of light falling at a unit distance from the optical center. Right? Right. So this is the power of lens is defined as the tangent of the angle by which it converges or diverges a beam from a light falling at a unit distance from the optical center. It means that this distance should be unit. This h must be unit, 1 unit, right? Then if one unit, and if you take a parallel light beam, then passing through this lens, obviously it will passing through F, and this distance is F, right? So if you take this, so more systematically we can say that tan alpha, here this tan delta is your power. P should be written like this. P is equal to tan alpha. But what is tan alpha? So tan delta, P is equal to tan of this angle, this delta angle. So that is equal to opposite, that is H by F will be taken. P is equal to H by F. But how much is H? And should the light ray should be from here or from here or from here? No, it should be from 1 unit. If it is in a meter, it should be taken as 1 meter. So therefore, P is equal to, in SI unit, it should be defined 1 by F. In SI unit, P is equal to 1 by F, where the unit distance is 1 meter and this power is the unit SI unit of power is per meter, 1 by meter, no, 1 by F. So in the same way, it is also it can be called by another term called as a diopter or diopter, right? So it is sometimes it is written as a 1D and 1 meter per 1 per meter, right? So usually when you go to hospitals or for eye specialist, they prescribe and they usually they write it as a plus 0.25 or minus 0.25 or else plus 1.25 or minus 2.5. So these are all measurements are in terms of diopter. If it is positive, then it is a plus. It means it's a convex lens you are supposed to be used, or if it is a negative, it is a concave lens you are supposed to be used, right? So in this way we can find out. Now let us go for a combination of thin lenses. If you take two lenses together and keep like this, then if you take this is object distance and image distance is a final object distance and final image. Suppose object distance is same for both, and whereas the V is a final image distance and V1 is image distance for this one, for first lens, that is A, and object distance for second lens, that is for B. Now let us use the lens formula for first one, and we see this one, that is 1 by V1, 1 by V1, this one, 1 by V1 minus 1 by U is equal to 1 by F. In the same way, if you apply the same lens formula for the second one, we will write this 1 by V, because this is a final image formed, right? So this is the V will be taken final image distance. 1 by V minus 1 by V1. Here, let me write here. You can see here. The first one is this for first lens. So this is the formula, that is 1 by V1 minus 1 by U is equal to 1 by F. And for second lens, we will use this one here, that is 1 by V final image minus this virtual image minus 1 by F, V1 will be taken, that is equal to 1 by F will be taken, right? So combining these equation 1 and 2, we can write this thing. If we add these two together, then we will write like this, then this will get cancelled, and this one and this one, sorry, right, this one as well as this one get cancelled, because this is my negative and this is positive, they get cancelled. What is left out is 1 by V and 1 by minus 1 by U, that we will write it here, 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2, like this. So but suppose if you replace this combination of lenses by a single lens here, right? What is the focal length of that? It is a combination of these two lenses, that is 1 by F. So substituting in this equation, suppose replace this by a single focal length, then you will get 1 by F here. That's what we do here. So therefore above equation, if you write like this, then you can write like this. 1 by F1 means for example, if you in place of these two, I keep another lens. It is act like these two effective lens of these two lenses. Then if you keep an object here, same object distance U, then where the image should be formed? Same only here. Image should be formed at here. Then image distance should be same. Here is the object distance is same, and image distance is same, and image length is same, and its focal length is the effective combination. So then if you substitute, then object distance and image distance are same, but focal length is F, and from 3 and 4 we can write like this, that is 1 by F is equal to 1 by F1 plus 1 by F2, right? Even in terms of power also you can write this. The effective power of a combination of two lenses can be written as P is equal to P1 plus P2, where P1 and P2 are power of individual lenses. In the same way, if you have number of lenses, right, if n number of lenses are there, then the effective power can be written as P is equal to P1 plus P2 plus P3 dash 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 Pn. The same way, in terms of focal length also we can write it 1 by f is equal to 1 by f1 plus 1 by f2 plus 1 by f3 dash 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 1 by f1 fn. Like this you can use. Then after this, let us pass on to refraction of light through a prism. Before that, we must understand the prism, right? It usually is called as a triangular based prism. Suppose if you see here, if you are having a prism here, the prism have two triangular surfaces. One is this one, another. These are called bases, and there are refracting surfaces here, which are in rectangular in nature, right? So this is one surface, and this is one surface, and this is one surface. These three are refractive surface. Whereas in case of some practical prisms, one will be in rough shape, that will be taken as base, and these two are taken as a refracting surface. So here, when light ray will be passing through this, then another light ray will come like this, right? Okay. So therefore, let us see how the light rays are passing through this, and what are the advantages of using prism, and all those things we'll see. Now let us see refraction of light through a prism. Okay. Now you see here. Here ABC. ABC is it's appeared to be a triangle. It is not triangle. It is we'll take it as what a cross section of prism. I used to say that is a cross section of prism. Means if you cut this into number of slices, you will get one slice. That one slice what I am is written there. That is ABC. ABC like this, right? Then if a light ray is passing through this in this manner here, if a light ray is passing through this, then it will undergo refraction, then it comes out like this, undergo refraction and comes like this, right? So to see that one, you have to see in this manner. The same way here, this is incident ray, then this is refracted ray, this is emergent ray. And here N1O is normal, and N2O is also normal, drawn at this point of incident and this point of incident at this point. Now if you take this extension of this one, the light ray is passing through this like this. Okay. Now let us consider a quadrilateral here, APOQ. In this quadrilateral, you see now angle between APO and angle between AQO is right angle, because these two are normal. If these two are 90 degree, the sum of these two is 90 degree, 180 degree. Then obviously angle between A and O, sum of angle between A and O must be 180 degree. That is what we will write here. In quadrilateral, we can write it as angle A plus angle O is 180 degree. Then now in this triangle, let us consider this triangle here, and this is I and this is R. This is R1, and this is R2 here. Right, in this triangle, we can write angle O plus angle R1 plus angle R2 is 180 degree, because the sum of the angles of a triangle is 180 degree. That's what we will take it. Now you see equation 1 and equation 2. You can see here, right? Angle A plus O is equal to 180 degree. Angle R1 plus R2 plus O is equal to 180 degree. So here something plus O is equal to 180 degree. And here also some other thing plus O is equal to 180 degree. So therefore from 1 and 2, what you can say that something must be equal to some other thing. What is that something? A. What is some other thing? R1 plus R2. So therefore from these two equations, we can write it as R1 plus A is equal to R1 plus R2. Okay, A is equal to R1 plus R2. Then here, right, so now here let's go for this angle of deviation. Angle of deviation means when a light ray is due to in the absence of this prism, the light ray would have gone like this. But due to presence of this prism, what will happen? The light ray is going like this. So therefore, the light ray has taken a deviation in this manner. So therefore, angle between incident ray and the emergent ray is called as angle of deviation. It is denoted by delta. So that is equal to you can write here this angle delta is equal to these two angles. This angle is angle I minus R1. This is R2, no? So therefore, this is angle I minus R2. By using exterior angle property, we can write it as delta is equal to I minus R1 plus E minus R2, right? So summing these two, delta is equal to 1 I plus E minus R1 plus R2, you can write. Call this equation number 3, right? From 3 and here by using this A, you can write like this, delta is equal to I plus E minus A, right? So that is, you can write it as I plus E is equal to A plus delta, you can write. Here fantastic things you can observe that for different angle of incidence, if you obtain a different angle of emergence, and for angle of prism A, where A is angle of prism, capital A, and we will get different angle of deviation also, right? And if you draw a graph of angle of deviation versus angle of incidence, then we get here like this, a curve like this, right? Wonderful thing is you see that for a particular angle of deviation, suppose if you take this one here, for a particular angle of deviation, there will be two angles will be there, corresponding angles, this angle and this angle. So either one will be angle of incidence and other will be angle of emergence, right? In another way, we can note that, for example, here if you consider here, and I will go back and see this one here, like this, right? Suppose if this is the angle of incident and this is the angle of emergence. In the same way, if you pass a light ray here back like this, then this will be angle of incident and the light ray will go like this. So this will be angle of emergence. So therefore, if for example, if this is 30 degree and this will be 48 degree, right? So I is 30 degree and E is 40 degree. In the same way, if I is 38 degree and this will be, sorry, I is 30 degree and 48 degree. So therefore, if I is 48 degree, then this will be 30 degree, right? So therefore, if angle of incidence is 30 degree and the angle of emergence will be 48 degree. But in this case also, angle of deviation will be same, right? So this is the incident ray, this is the emergent ray, then angle of deviation will be this much, right? So therefore, so here you will get it actually. Just I will draw and show you. Okay, so here you will get this angle. So this will be angle of deviation here, right? And these two angles are equal, obviously, right? So therefore, and if you see here, and we note that if this is here, you can see for a particular angle of deviation, there will be two different angle of incidence. Means if you incident at, for example, if you incident at this angle, emergence will be this much. If you incident at this angle, emergence will be this much. So therefore, they are interchangeable, and even from this equation also we can note it also. So for example, if you come back and see now from this equation, see here, if I and E are interchanged, then A will be constant and delta will be same, right? So therefore, and but at the same time, if you keep on increasing the angle of incidence, you will get a curve like this. But at this point, you note here where the angle of deviation is minimum. This is called as angle of minimum deviation. At this angle of minimum deviation, we can note that, as I told you, that this is incident angle and this is emergent angle. In the same way, if you draw another curve here, right, and here you draw a curve. This is incident angle and this is emergent angle. And similarly, if you draw here, right, this is incident angle and this is emergent angle. Otherwise, if this is incident angle, this will be emergent angle. So therefore, at this point where you can note that angle of incidence and angle of emergence are same. So therefore, the angle of deviation is minimum and if I is equal to E. Otherwise, so at I is equal to E, the angle of deviation is minimum. Otherwise, if angle of deviation is minimum, then we can see that angle of incidence is equal to angle of emergence. So based on this property, we can note that suppose at delta M, I is equal to E, and at the same time, if I is equal to E, obviously R1 is equal to R2. Let to go back and see that this is. If I and E are same, then obviously R1 and R2 are also same, right? So therefore, refractive index of the material of the prism can be written like this. That is, now we can obtain. Suppose if delta m is equal to delta m, right? I is equal to E and R1 is equal to R2 is equal to R, you can say. And substituting this, you will get like this. So in the previous equation, you got A is equal to R1 plus R2. Here you can see this. So here, right? A is equal to R1 R2, you got it, right? Then I can be written like this. I plus E is equal to A plus delta. And I and E are same at the angle of minimum deviation, at the condition of angle of minimum deviation. So after this, we can write R is equal to A by 2 and I can be written here. And I and E are same. So therefore here you can write it as 2I, right? 2I is equal to A plus delta M. Then I can be written as A plus delta M by 2. Then using Snell's law, we can write like this. Mu is equal to sin I by sin R. That is sin I by sin R. That here you substitute this. R you substitute here and I you substituting here. Then you will get mu is equal to sin A plus delta M by 2 and sin A by 2. So this is the equation for where mu is the refractive index. By using this equation, we can find the refractive index by knowing angle of prism and angle of minimum deviation. Otherwise, was also, right? So then after this, let us go for the refraction by a small angle prism for small angle of incidence. Right? If it is a small angle of incidence, the same equation here, if you see that this one, you can instead of writing sin A plus delta M by 2 and sin A by 2, you can write it as A plus delta M by 2 and A by 2. Then 2 to get cancelled, then you can write it as A plus delta M by A. Then here, then instead of that, here you can write it as yes. You can write it as mu is equal to A plus delta M by A. So that is mu is equal to 1 plus delta M by A. So therefore mu minus 1 is equal to delta M by A. So therefore A into mu minus 1 is equal to delta M. So therefore we can obtain for small angles, we can use this one also, right? Otherwise mu is equal to A plus delta M by also can be used, right? So the same thing we will write here. Then mu is equal to size, that is, it can be obtained in another manner, and delta is equal to A into mu minus 1. Then after this, another wonderful phenomenon we can go, that is dispersion of white light. So from lower class itself, we have come to know that by different activities or experiment, that when you pass a white light through a prism, then the prism will give different colors, and there are different stories about this. Well, I am not going to for this, and let's directly will go that. When a white light is passing through the prism, then the prism will give different colors, which is having that white light. Right, the phenomenon of splitting of white light into different constituent colors is called as dispersion of light. This band of colors is from violet to red, that is Vibgaya, violet, indigo, blue, green, yellow, orange and red. Right, so let us see this, how this, where let A, B, C be the cross section of prism. If you pass a white light here, right, then you can see here how it goes. Right, but reason is this, white light contain all these colors, but when they passes from one medium to another medium, they undergo different, they will deviate in different with different angles. So because of that, they will be separated. Right. Further, when they are traveling from one this prism to air, they will be further separated. And at the same time, if you draw back this and you see that this angle of deviation will be different. This is delta R is the angle of deviation for red color. In the same way for violet, if you try here, delta V is the angle of deviation for violet color. So which angle is have more? Obviously delta violet, that is the angle of deviation for violet color will be more compared to angle of deviation for red color. Right? So in this way we can see that we can write mu V is equal to sin A by sin RV, that this is. Then mu R is equal to sin I by sin RR. And at the same time, the refractive index of the prism will be different for different color, because angle of deviation will be different. Delta V and delta R different, and even angle of minimum deviation also will be different for different color. Then obviously the refractive index of this prism will be different for different color, right? So in the previous section, whatever we have discussed is only for particular color or for a given color, right? But here the refractive will be different. So since mu V is greater than mu R, we can let R is greater than RR is greater than RV. Otherwise also you can see here, say angle RR, refractive index of angle of refraction for red color and angle of refraction for violet color. You can note it here, right? Now after this, we'll pass on to another phenomenon that is called scattering of light. Scattering means in a simple way that the light will be move in a different manner, different direction, all the possible direction. When a light travel incident on the surface, then it will scatter in all the direction, right? For example, if you say here, then when a light falls on this, then because of this surface, the light will be scattered. Scattered in the sense it will, after incidenting, it will go in different direction. So based on the surface, right? So another wonderful phenomenon is because of this scattering of light, we are able to see each other. Because if at all if there is no such scattering of light, then it is very simple. In a room, sitting in a room, you will not find a light unless you put on your a tube light or fluorescent light or this LEDs and all those things, right? So therefore, and it is then what the scattering phenomena is and how this scattering takes place means when light travels in a medium or an atmosphere, then light will be while passing through the atmosphere, the light will be incident on the molecules of the atmosphere. What it may be oxygen or molecules of the atmosphere. Then the light will be scattered in different directions. And the scattering, the amount of scattering is depend upon the size of the molecule, right? If size of the molecule is larger, and the scattering will be larger. If size of the molecule is smaller, then it will be scattering will be less. And also it depends upon the wavelength, right? The different colors wavelength are scattered in different manner. Then as per Rayleigh, we come across here, right? This is, we call it as Rayleigh scattering is proportional to 1 by lambda to the power of 4, right? So as the wavelength increases, the scattering decreases. In the same way, if you go for VIBGYOR, violet scatter more compared to red, right? Because red color has a longer wavelength, so longer wavelength color scatter less compared to a shorter wavelength. So if you take VIBGYOR, then violet will be scattered more compared to this red color. Then next question comes, why the color of sky is blue, right? So as per this statement, we know that white light obtained from the sun falls on the molecules of the air, but the air molecules scatter all these colors, but the maximum will be scattered by this violet, indigo and blue, but the least scattering will be red color, right? So but at the same time, violet and indigo are less sensitive to our eyes, but blue is a predominant color, so that is more sensitive to our eyes, so that we are able to see that the color of the sky is blue. And at the same time, because of that, then the sea is also will be seen as blue, right? Then this scattering phenomena can able to explain other phenomena. And one more thing here, that when looking at the sky, sun received, then one more thing, receives scattering sunlight shorter wavelength predominant, and giving sky is scattered in bluish color. And in some clouds and all, what will happen, the size of the molecules is very larger in size. Because of that, they scattered most of the colors. Because of that, what will happen, it will appear to be white in color. Then after this, we will go for another thing, that reddish appearance of sun during sunrise and sunset. So during sunset and sunrise, we see that the color of the sky is in a red color or a reddish or orange in color. Then why it is so? So because a very simple reason is that because of atmospheric refraction, simple way. Number one. Number two, then the same atmosphere will be there in daytime also. Why it is not like that? Because here during this sunrise and sunset, suppose you will be here. Suppose you will be here at this position. Right? So this light obtained from this sun will reach to this one, a person who is standing here. Right? So therefore what will happen, it is the light has to travel a larger distance of atmosphere during sunrise and sunset. Right? But whereas in daytime what will happen, this much atmosphere it has to travel. You can see here, this much. Right? But whereas in morning and evening it has to cover this much atmosphere. So because of that what will happen, the most of the colored light rays will be scattered and eliminated out. When because of that what will happen, the left out will be longer wavelength, that is red or orange color. The red or orange color will reach to you people, so that you feel that color of the sky is red or orange.
Our planet Earth is surrounded by a layer of gases called the atmosphere. When sunlight enters the Earth's surface, it is deflected from its original path by dust particles and gas molecules. This process is called light scattering. The amount of light that is scattered depends on the wavelength of the light. The wavelength of colored lights decreases from red light to violet light. The shorter the wavelength of the light, the more it will be scattered. Blue light, which has a shorter wavelength, is scattered more than red light in the atmosphere. In fact, the shorter the wavelength of the color, the more it is scattered in the atmosphere. The distance that sunlight must travel through the atmosphere before reaching our eyes also affects the amount of light that is scattered. This distance depends on the time of the day. During sunrise, when the sun is close to the horizon, the path of the sunlight in the atmosphere is the longest. At noon, when the sun is high in the sky, the path of the sunlight in the atmosphere is the shortest. During sunset, when the sun is close to the horizon, the path of the sunlight in the atmosphere is the longest. At night, the sky is dark because sunlight cannot reach the observer. The occurrence of blue sky during the day and red sky during sunset is due to the scattering of light. During daytime, blue light scatters more than red light in the atmosphere, and due to the shorter distance traveled, it is able to reach our eyes before being completely scattered away. As a result, we can see blue light coming from all parts of the sky, causing it to appear blue. During sunset, sunlight travels a longer distance in the atmosphere. This means that most of the blue light will be scattered, while some red light will reach the observer's eyes, making the sky appear red.
Right, after this, we'll go for another topic, that is optical instruments. Right, in case of optical instrument, the first one is simple microscope. Simple microscope is this, a common simple convex lens or a converging lens is called as a simple microscope. In this simple microscope, it will be used as a magnifying glass. Suppose if you take an object here between the principal focus and optical center, then what will happen when you keep an object here? Suppose this is a lens here, this is a lens, and this is optical center. This is a lens, optical center with optical center, and this is a principal focus. Then when you keep an object here, then what will happen? When you see from this side, it forms a virtual image, but in this manner, erect manner. So because of that, the image formed is virtual and magnified. So that magnified image will be seen as a magnified image seen from the other side is useful to see some other things. Usually in case of this watch making shops and watch bearing shops, or in some other in goldsmith and all, they'll use this simple lens as a magnifying glass. And the magnification is depend upon the focal length of this. Let us see this how it will be obtained. And here you can see magnification, and we know that m is equal to v by u. In the previously during this discussion of lens, we have noted that. So magnification is equal to v by u. Then v is equal to 1 by u. Then if you take this 1 by v, u can be written as 1 by v minus 1 by f. And one more thing here, then whenever you are keeping a lens here like this, you will see that this the image should be formed at a distance of least distinct vision, not beyond that. If it forms at beyond, it will be a very enlarged image you will get, but the blur image you will not get the clear image. To see the clear image, the image should be formed at a distance of least distinct vision. That distance of least distinct vision, usually for a normal person, it is 25 centimeter. So therefore that distance is denoted by capital D. Then the image forms at D. So then substituting in this equation, here you will get it as 1 v, if you take it inside, you can write it as 1 minus v by f, right? But v is minus d because in the same side, this is the incident ray and the image forms also in the same side. So therefore you write it as minus d. So after substituting that, you will get 1 by 1 plus d by f. So therefore the magnification obtained for this simple magnifying glass or simple microscope is 1 plus d by f. After this we will go for compound microscope. In case of compound microscope, we use two lenses here, right? These two lenses, one is objective, another one is eyepiece. Where the objective is that when you keep an object here, the objective is the lens which is nearer to object, that is called as objective. Then the lens which is nearer to eye is called as eyepiece. So now let us see here. Then f0 is the focal length of objective and fe is focal length of eyepiece here. Now in case of compound microscope, the object has to be placed between 2 f0 and f0, right, such that it forms a real image here, and real inverted and enlarged image will be formed. You can see here it forms a real and enlarged image, a dash b dash here. But at the same time, now what we have to do is you have to keep this eyepiece. It should be adjusted. It should move forward and backward, such that the image formed by this objective should lie between eyepiece, focal length of the eyepiece, and the optical center of the eyepiece here in between. So because of that, what will happen? It forms a virtual image here. It forms a virtual image, inverted but enlarged. You see here. So it forms like this. So it forms a virtual and a inverted image. Right. So therefore, in this case, how to get a magnification? Right. So magnification may not be asked in the examination, but at the same time, let us see that how it will be obtained. The converging lens nearer to the object is called as objective, and the lens which is close to eye is called eyepiece. Right? Let us see. That is called as angular magnification or magnifying power. The angular magnification is the magnification or it is the ratio of angle subtended by the image at the observer to the angle subtended by the object at the observer. So let me go back and see that. So here you see now, suppose this is an object and its subtends an angle here. Its subtends an angle. That angle we will note it as angle subtended by the object. Then here the image subtends an angle. This is at beta, right? So when both are kept at a distance of least distinct vision. So therefore, it is an angular magnification can be obtained. That is, you can see here. It is the angle subtended by the image at the final image to the angle subtended by the object at the observer's eye directly when both are placed at a distance of least distinct vision. Right? So therefore, we write it as magnification m is equal to beta by alpha. Therefore, where alpha, instead of finding alpha, we will go for For small angle, alpha is equal to tan alpha and beta is equal to tan beta. Therefore, magnification can be written as tan beta by tan alpha. So therefore, here let us go back. M is equal to magnification of tan beta. Let us go back and see now. Here you see. So magnification beta. Beta is, this is tan beta. Tan beta is opposite by adjacent. So therefore, A dash B dash, sorry, A double dash B dash by A dash P, right? And at the same time for alpha, this is A triple dash by A double dash by AP, we'll write it, right? So we can see these things here. That is A double dash B double dash by D. And since it is tan alpha, you will write it as 1 by A double dash A triple dash by D. That's D goes to numerator here. We will write it here. So therefore, then in this distance is least distance of distinct with these will get cancelled. So therefore, we write it as A double dash B double dash by A double dash A triple dash here. So therefore, A double dash B double dash and A double dash A triple dash can be written as AB here. Right, I will go back and see now. So here, A double dash A triple dash, this height is same as AB, right? So that's what we will write here. Okay, then we see. Okay, so DD get cancelled. Then we'll left with the A double dash B double dash by AB. Right, A double dash B double dash by AB can be written as here. A double dash by B double A double dash B double dash by A dash B dash into A dash B dash by AB. So this A double dash by A dash B dash is the magnification produced by eyepiece, and this A dash B dash by AB is the magnification produced by the objective. So therefore, that we can write it as M is equal to ME into M naught or MO, objective. So therefore, but we know that ME is as same as in a simple microscope. That is ME is equal to 1 minus VE by FE, we write it. Then objective, and ultimately we write this as ME is equal to 1 plus D by FE as we obtained in simple microscope. Then M naught can be written as minus V naught by U naught. This is A dash B dash by AB can be written as V naught by U naught. In case of lens, we write it as V naught by minus U naught. So therefore, substituting this one and this one, both substituting this M naught and substituting this ME in this equation, right? We obtain here M is equal to V naught by minus U naught into 1 plus D by FE. So now let us see this V naught. V naught is the image distance obtained by the objective, and U naught is the object distance of objective. So U naught is usually what we do is to get a maximum focal length. What we do is we can keep this here. What we do is we keep this much closer and closer. You will get a highly magnified image. So magnified image is much better to get a highly magnified image at the final image. To get final image, highly magnified image, it will help. So therefore, we keep this object very much close to F naught, but between F naught to F naught and F naught. So therefore, this distance, object distance U naught can be written as FO, F naught. So similarly, let me come back here. Right, and V naught is the length of the tube. So that because that is between the first lens and the second lens, that is objective and image lens, sorry, eyepiece. So as a overall, substituting these two in this equation, then we can write like this: M is equal to minus L by F naught into 1 plus D by FE. So therefore, for normal adjustment, the image forms at infinity, then we can write this: M is equal to minus L by F naught into D by FE. right? So this is all about how the magnification of my compound microscope can be obtained. And after this, another important thing is astronomical telescope, right? In case of astronomical telescope, the difference between astronomical telescope and for a normal telescope is that the image obtained is in the erect position, in the same position, same way. But whereas in case of astronomical telescope, the image obtained is inverted one to get a highly magnified image. Let us see this, and first we will see that the image forms at infinity, and next we will see the image forms at a normal adjustment. So in case of astronomical telescope, there also we come across objective and eyepiece. But whereas one thing you must note that the objective must have more aperture so that it gathers light as much as possible so that it forms image, a high intensified image and a highly magnified image. Then here the eyepiece is moderate one and shorter focal length here. So like this he kept, then let us consider that an object is far away from these two lenses, that is astronomical telescope. Then whenever the object is far away from the eye objective or from both this telescope, both the lens or telescope, then it forms an image at a principal focus of objective, right? So therefore it forms image at f naught only, and at the same time what we do is we keep this eyepiece should be adjusted, move forward and backward such that the image formed is between f naught fe and pe. Image formed is between fe and pe. If it forms exactly at fe, then what will happen? The image forms at infinity as like this. The image forms at infinity, right? And at the same time you can note this f naught is the distance between the principal focus of objective and f naught, and this small fe is the focal length of the eyepiece, that is distance between fe and pe, like this, right? And the distance between these two lenses, you can write it as a length of the tube, that is f naught plus fe, here you can see, right? Then the angle subtended by the object at the eye, whether it is in the objective or eye, is one not the same because it is far away from us. So here is alpha and here also alpha only. So this we can write like this. This is alpha. If this is alpha, obviously this is also alpha. Then this is beta because the angle subtended by the image at the eye. So based on this we can obtain the magnification. Right. One thing we should know in between before that, focal length of the objective is much greater than that of the eyepiece. So objective must have more focal length than the eyepiece. Then aperture of the objective is also larger as compared to eyepiece, as I told you, so that it can gather more light. Suppose when you are focusing at Jupiter, then it has to take more light to obtain from the Jupiter so that it forms the image of the Jupiter, like this, right? And this eyepiece also forms an image at distance only. We can see that the Jupiter, once you focus to Jupiter, the image forms at infinity only, far away from us, like this. So the magnification here also same thing, but only thing is that infinity, right? The angular magnification in case of telescope is, it is a ratio of the angle subtended by the image at the eye to the angle subtended by the object at the eye when both are at infinity here, right? So therefore magnification m can be written as beta by alpha, and similarly instead of writing beta by alpha we will go for tan alpha by tan beta by tan alpha. That's what here magnification is equal to tan beta by tan alpha. Then m is equal to fe by fei by fe into fe. Let us see now tan beta. What is tan beta? Let's see. Tan beta is fei by fep or PEF, right? Let us see here. This is tan beta is fei by PEFE. Then tan alpha. Let us go back and see. Tan alpha is this. Actually, it is this. And since these are vertical opposite angles, we can use this triangle IFE T or IF naught T also we can take it. So therefore, that is IFE by T naught FE like this, right? Opposite by adjacent. So hence it forms here like this. Okay. So FEI by P naught FE. So then here we can write it FE into I. FEI by PFE. What is FEI and what is FEI? Both are same, right? If you take same distances there, then we can write it as if height of this is I. If this height is taken FE by I, both are same, but only thing is both are in negative direction because it is downward. So minus I or minus L by minus I by FE. This is also minus I by FE. Otherwise, you can write the same thing, that length, and here these two get cancelled. So ultimately, we can write like this: minus F naught by FE is the magnification. Then after this, let us go for how the image formed for at a distance of least distinct vision and what is the magnification we will obtain here. So as usual, same only, but here object is also at infinity, and infinity means far away from us. Then same thing here, F naught, FE, F naught and FE and is same like this, and here it forms image at F naught. But here what we do is we adjust this eyepiece, move forward and backward such that it forms image at least distance of distinct vision. You can see here. These are the light rays, and light ray passing here and forms image, and further they move forward and they pass through this lens. Then they go like this. So you, while constructing or writing this figure, you must keep in mind that they should pass through this lens, and after that only they will bend. And it forms image here like this. So you can see image forms at a distance of least distinct vision. This is right, AB like this. Then let us take this alpha. If this is alpha, it is the angle subtended by the object at objective, or eyepiece also same. But here we will take alpha, and this is also alpha because of vertical opposite angles, and where beta is the angle subtended by the image at I. So like this, then we'll go for angular magnification. Same is the formula, but here at distance of least distinct vision. But angle is at object is at infinity. So therefore, it is a ratio of the angle subtended by the image to the angle subtended by the object, right? The final image formed at least distance of distinct vision to the angle subtended by the by the object lying at infinity when seen directly. Therefore, magnification can be done as beta by alpha. That is, here instead of beta and alpha, we can write it as tan beta by tan alpha. So that is m is equal to tan beta by tan alpha. Then m is equal to tan beta, same like previous one. That is tan beta is f naught I by p f naught plus by f naught I by p naught f naught. Let me go back and see now here. This is f naught I by p naught p f naught. F naught I by p f naught. Okay. Then for alpha, f naught I by p naught f naught. F naught I by p naught f naught will get it. Then magnification here. We can see that f naught I get cancelled. Then what is remaining is p naught f naught by this one. This goes to numerator here. P naught f naught by p f naught. Or else here we write it as p naught f naught. Where is p naught f naught? You see this. P naught f naught is this, right? So this is the focal length, but is focal length of objective, and it is positive. We take it as plus f naught. And whereas this one, this distance f naught p is taken as an object distance for this lens. That is UE, you take it, right? We'll see here. UE but minus, because in the left side, in the direction of the light passing through it. So then by using this, we will substitute for 1 by ue, 1 by minus ue will go for this equation, and we see here we know the length equation, that is 1 by v is equal to 1 by minus 1 by u is equal to 1 by f. So therefore minus 1 by u can be written like this, and whereas v is distance of least distant division, so in place of v you write it as minus d, then minus of 1 by u, that is minus ue you write it, that is equal to 1 by fe you write it. So therefore you take this and take to the other side, then we will get like this, you see 1 by minus minus get cancelled, plus then 1 by ue is equal to 1 by fe plus 1 by d. So therefore we can write this one here, m is equal to and substituting this one f naught as it is, we write it here, okay, then minus f naught will write it, only 1 by ue will write it, 1 by ue is 1 by fe plus 1 by d, and this I'll write here and you will understand a little more clear here. So actually we write it as m is equal to minus f naught into 1 by fe plus 1 by d. So that is equal to minus f naught by fe. Fe is taken in outside. Then what is left out here is, it is 1 plus, since fe is not in the numerator, we put fe here, fe by d. So we'll get the same equation here. So therefore overall magnification of this magnification of telescope is m is equal to minus f naught by fe into 1 plus fe by d. After the refraction type of telescope, there is another kind of telescope called as a reflecting type of telescope. There are different types of reflecting type of telescope. One is Newtonian reflecting type of telescope, Cassegrain reflecting type of telescope, and so on. But these reflecting type of telescope has more advantages. One of such advantages is it get away from chromatic aberration, and it forms a brighter image, because since it is not undergoing any refraction, whenever any light undergo refraction, the intensity loss will be there. But whereas in case of reflecting type of telescope, there is less intensity loss will be there. And another one is it is easily portable from one place to another place, and it also less cost, because if to prepare a lens of a very big huge aperture, it requires more cost. So reflecting type of telescope has a less cost also. Then one of such reflecting type of telescope is Hubble telescope, which is in space, which captures the images of celestial bodies, and it is keep on sending the images to Earth even today, right? With this we are completing this chapter, that is ray optics. Thank you.